Imagine standing on the edge of a vast ice sheet, stretching as far as the eye can see. The wind howls around you, whipping snow into spiraling patterns across the frozen landscape. This is not the Arctic or Antarctica of today. This is your home, the Northern Hemisphere, just 12,000 years ago. The world you know would be unrecognizable then. Much of North America, Europe, and Asia lay buried beneath ice sheets 2 miles thick. Sea levels were hundreds of feet lower. Massive creatures, woolly mammoths, saber-toothed cats, and giant ground sloths roamed landscapes that no longer exist. And then something happened. Something catastrophic. In what amounts to a geological eye blink, our planet underwent a transformation so sudden and so profound that we're still struggling to understand it today. Earth teetered on the edge of an abyss, and human civilization hung in the balance. The puzzle begins with a simple observation. Around 12,900 years ago, just as the Earth was warming and the great ice sheets were retreating, temperatures suddenly plunged. Our planet was thrust back into a deep freeze that lasted over 1,000 years. Scientists call this period the Younger Dryas. What could possibly cause such a dramatic reversal? The conventional explanation that melting ice disrupted ocean currents has never fully satisfied researchers. The change was too abrupt, too extreme, too global in its effects. Something else must have happened. Recent discoveries have unearthed startling evidence. A thin layer of unusual materials spread across 4 continents precisely at this time. Tiny diamonds, metallic microspherules, and exotic elements not typically found on Earth's surface. These materials tell a story of extreme heat, pressure, and catastrophic force. The implications are staggering. We may be looking at evidence of an extraterrestrial impact event that dwarfed the asteroid strike that killed the dinosaurs. An event so devastating it triggered continent-wide wildfires, massive flooding, and the extinction of dozens of large animal species. But here's the most unsettling part. This didn't happen in Earth's distant past. It occurred when humans had already spread across the planet, when we were already building settlements, developing agriculture, and laying the foundations for what would become civilization. Legends and myths from around the world speak of this time. Stories of fire raining from the sky, of great floods and darkness, of a time when the gods nearly destroyed humanity. For centuries, we dismissed these as primitive fantasies. Now, we're not so sure. Tonight, we'll explore the mounting evidence for a cosmic catastrophe that nearly ended human civilization before it truly began. We'll examine geological findings, ancient legends, and the latest scientific controversies surrounding this pivotal moment in Earth's recent history. We'll trace how this event may have reset the clock on human development, forcing the survivors to rebuild from scratch. And we'll consider a sobering possibility that what happened once could happen again, with consequences even more dire for our technologically dependent world. The story of the Younger Dryas Impact Hypothesis is not just about our past. It's about our present vulnerability and our future survival. It forces us to reconsider humanity's place in the cosmos and our relationship with catastrophe. As we journey through the evidence, you'll encounter passionate scientists on both sides of this debate. Some see proof of a world-changing impact. Others see misinterpreted data and wishful thinking. The scientific community remains divided, the controversy still raging. What's beyond dispute is that something extraordinary happened 12,900 years ago. Something that left its mark in the geological record, in the distribution of animal and plant species, in the trajectory of human development, and perhaps even in our collective memory. You're about to discover why the transition from the last ice age to our current warm period wasn't the gradual, peaceful process once imagined. Instead, it may have been a time of fire and flood, of extinction and survival, of endings and painful new beginnings. The truth is both humbling and frightening. Civilization as we know it may exist because of, and despite, a cosmic catastrophe that nearly wiped us out. A catastrophe that could have turned Earth into a very different kind of planet, one on which humans might never have flourished. Tonight, we dive into the gap that science still cannot fully explain. We'll examine the evidence for an apocalypse that may have shaped not just our planet, but our very identity as a species. And we'll ask what it means for our future on this fragile blue world. Welcome to a journey 12,000 years into the past, to a moment when the trajectory of life on Earth hung by the thinnest of threads. A journey to understand how close we came to never existing at all, and what that means for our precarious present. This is the story of when the world almost ended. Chapter 2. The Great Turning Point. The date 10,900 BC might seem unremarkable. No written records exist from this time. No great monuments stood. Yet this moment may represent the most significant turning point in human history, since we first emerged as a species, a cosmic catastrophe that reset the clock on human development. To grasp the enormity of what's at stake, we need to understand what the Younger Dryas Impact Hypothesis actually proposes. The theory suggests that fragments of a disintegrating comet or asteroid struck Earth, causing widespread devastation and triggering a return to Ice Age conditions. If true, this hypothesis would rewrite our understanding of human history. It would explain why advanced societies seem to emerge suddenly in the archaeological record, rather than through gradual development. The survivors of this catastrophe would have carried the memory of previous achievements. The conventional narrative of human progress tells us that civilization developed slowly, with agriculture emerging independently in different regions as the climate stabilized after the last ice age. This gradual view has dominated academic thinking for over a century. But what if this narrative is wrong? What if human development was not slow and steady, but punctuated by devastating setbacks? What if we've been climbing out of an abyss rather than ascending steadily from primitive origins? The evidence challenges our most fundamental assumptions about who we are and where we came from. It suggests that human history is not a story of steady progress, but one of catastrophe and recovery, destruction and rebuilding, forgetting and remembering. The stakes extend beyond academic debates. If the Younger Dryas Impact Hypothesis is correct, it means our planet remains vulnerable to similar events. The relative stability we've enjoyed for the last 11,700 years, the period geologists call the Holocene, may be the exception rather than the rule. This vulnerability carries profound implications for how we think about planetary defense, climate stability, and the fragility of civilization. If a cosmic impact could nearly end human development once, it could happen again, possibly with even more devastating consequences in our interconnected world. The mystery deepens when we consider the timing. The proposed impact occurred just as humans were beginning to transition from hunter-gatherer lifestyles to settled agricultural communities. Several proto-agricultural sites from before this time have been discovered, then mysteriously abandoned. Göbekli Tepe in Turkey, a massive stone temple complex dating to approximately 9600 BC, emerges just after the Younger Dryas period ended. Its sophisticated construction suggests it was built by people who already possessed advanced knowledge, perhaps survivors preserving what they could. Ancient myths worldwide describe similar catastrophic events: fire from the sky, worldwide floods, the destruction of previous worlds. From Native American legends to Mesopotamian epics, from Norse mythology to Hindu cosmology, the theme of world-ending disaster followed by renewal is universal. Could these myths be more than primitive attempts to explain natural phenomena? Could they be cultural memories of actual events, passed down through generations? If so, they represent the oldest historical records we possess, predating writing itself. The implications extend to our understanding of religion and spiritual traditions. Many ancient belief systems include apocalyptic scenarios and cosmic cycles of destruction and rebirth. These might not be mere metaphysical speculations, but responses to actual historical trauma. For archaeology, Accepting this hypothesis would require reconsidering numerous sites and artifacts. Places like Göbekli Tepe, the Sphinx, and various megalithic structures worldwide might need to be understood as remnants of recovery rather than initial development, rebuilding rather than building. The impact hypothesis also offers a compelling explanation for the sudden extinction of North American megafauna. Over 35 genera of large mammals, including mammoths, mastodons, giant ground sloths, and American camels, disappeared virtually simultaneously around 12,900 years ago. Conventional explanations attribute these extinctions to human hunting or climate change, but neither fully accounts for the suddenness and selectivity of the extinctions. A catastrophic event that triggered continent-wide wildfires would better explain this dramatic ecological collapse. For climate science, the implications are equally profound. The Younger Dryas period has long puzzled researchers because of its suddenness and severity. If cosmic impacts can trigger such dramatic climate shifts, our models of climate change may need significant revision. This reconsideration extends to how we evaluate current climate threats. Understanding past abrupt changes becomes crucial for anticipating future scenarios, especially as we push our climate system into uncharted territory through greenhouse gas emissions. What's at stake is nothing less than our conception of human capability and resilience. If advanced societies existed before the Younger Dryas impact only to be devastated, it suggests both the fragility of civilization and a remarkable human capacity to rebuild from catastrophe. The hypothesis challenges our chronological arrogance, the assumption that we stand at the pinnacle of human achievement. We may instead be reattaining knowledge and capabilities that existed before, slowly recovering what was lost in fire and ice 12,900 years ago. Most profoundly, this hypothesis forces us to reconsider our place in the cosmos. Earth is not isolated but part of a dynamic solar system where cosmic events can and do affect our planet. Our existence may be more precarious and perhaps more miraculous than we typically acknowledge. If proven correct, the Younger Dryas Impact Hypothesis would constitute one of the greatest scientific revelations in history. It would bridge disciplines from astronomy to anthropology, geology to mythology, and force a fundamental reconsideration of human origins. The controversy surrounding this hypothesis reflects its revolutionary potential. Established paradigms don't shift easily. Yet the mounting evidence demands we consider the possibility that everything we thought we knew about human beginnings might be incomplete. Chapter 3. The World Before the Fall. To understand what happened 12,900 years ago, we must first understand the world as it existed then. The planet Earth was emerging from the grip of the last glacial maximum, the peak of the most recent ice age, which had reached its coldest point around 20,000 BC. By 11,000 BC, the world was warming. Massive ice sheets that had covered much of North America, Europe, and Asia were retreating. Sea levels were rising as meltwater returned to the oceans. New landscapes were emerging from under the ice, creating opportunities for plants, animals, and humans. This warming period, known to scientists as the Bulling-Allard interstadial, saw temperatures in some regions rise to near modern levels. Forests spread north into areas previously covered by tundra. Large herbivores followed the expanding vegetation, and human populations moved with the herds. Human societies at this time were diverse and adaptable. While often characterized as simple hunter-gatherers, archaeological evidence suggests that some groups were developing complex social structures, long-distance trade networks, and the beginnings of plant domestication. In North America, the Clovis culture was spreading rapidly. Named after distinctive stone spear points first found near Clovis, New Mexico, these people were sophisticated hunter-gatherers who specialized in hunting large mammals, particularly mammoths and mastodons. The Nachifian culture flourished in the eastern Mediterranean, establishing semi-permanent settlements before true agriculture. At sites like Ain Malaha in modern Israel, they built circular houses, created art, crafted jewelry, and developed specialized tools for harvesting wild grains. In what is now Turkey, evidence suggests people were gathering at sites like Göbekli Tepe for purposes that may have been spiritual or ceremonial. The organizational capacity to create such structures indicates societies more complex than traditionally imagined for this period. Throughout Europe, Asia, and Australia, diverse human groups had adapted to their local environments, developing specialized technologies and social practices. The warming climate was creating conditions that would later allow for the development of agriculture and settled communities. The animal world was dramatically different from today. North America hosted an array of megafauna now extinct: woolly and Columbian mammoths, American mastodons, giant ground sloths, American lions, short-faced bears, and numerous other large species that have no modern equivalents. Similar assemblages of large animals existed on other continents. These creatures had evolved during the Pleistocene epoch and had survived numerous climatic shifts. Their sudden disappearance around 12,900 years ago represents one of the great mysteries of paleontology. The planet's geography was also different. Lower sea levels meant coastal plains extended much further than today. The British Isles were connected to continental Europe. Indonesia was joined to mainland Asia. Australia and New Guinea formed a single landmass called Sahul. North America and Siberia were connected by the Bering Land Bridge, a vast plain over 1,000 miles wide that allowed animals and humans to move between the continents. This crossing had enabled the peopling of the Americas, a process still ongoing during this period. The climate, while warming, was still more volatile than today's. Ice core records show rapid fluctuations in temperature were common during the Pleistocene epoch. However, what happened next was extreme, even by the standards of this geologically tumultuous period. Around 12,900 years ago, as the planet seemed headed toward interglacial warmth, something triggered a reversal. Temperatures plummeted, returning to near-glacial conditions in parts of the northern hemisphere. This cold snap, lasting over 1,200 years, is the Younger Dryas. The conventional explanation for this reversal involves meltwater from the retreating North American ice sheet. As this fresh water poured into the North Atlantic, it may have disrupted the ocean currents that transport heat from the tropics to the poles. However, this mechanism alone doesn't fully explain the abruptness of the transition or certain anomalous evidence found in sediments precisely at the Younger Dryas boundary. Something more catastrophic may have triggered or amplified the climate shift. The world before the proposed impact was one of transition and potential. Human societies were developing new technologies and social arrangements. Ecosystems were adapting to the retreating ice. The trajectory seemed to be toward conditions favorable for human flourishing. What happened next would dramatically alter this trajectory. The evidence suggests a cosmic impact or series of impacts that triggered continent-wide wildfires, atmospheric dust and debris, and possibly the failure of the North Atlantic circulation system. To understand the scale of this proposed catastrophe, we need to examine the physical evidence. Across 4 continents, at the precise layer corresponding to 12,900 years ago, researchers have found an unusual assemblage of materials that doesn't match normal geological processes. This boundary layer contains nanodiamonds, magnetic spherules, carbon spherules, melt glass, platinum group elements, and other markers consistent with extreme heat and pressure. Similar materials are found at known impact sites like Meteor Crater in Arizona and the Chicxulub Crater in Mexico. Particularly telling are the nanodiamonds, including a form called lonsdaleite or hexagonal diamond that forms under extreme pressure and heat, conditions typically found only in cosmic impacts or experimental nuclear explosions. These cannot be explained by normal Earth processes. The geographic extent of these materials is vast, stretching across North America, Europe, and parts of South America and Asia. This distribution suggests not a single localized impact, but multiple airbursts or impacts from fragments of a disintegrating comet or asteroid. No impact crater of appropriate size and age has been definitively identified, which skeptics cite as evidence against the hypothesis. However, proponents suggest the impactor may have struck the North American ice sheet, leaving no crater or exploded in the atmosphere. Recent discoveries at Greenland's Hiawatha crater have sparked interest, though dating remains uncertain. If confirmed to be 12,900 years old, this 31-kilometer impact structure beneath the ice sheet would provide powerful support for the Younger Dryas Impact Hypothesis. The timing aligns perfectly with both the climate reversal and the North American megafaunal extinctions. Something extraordinary happened at this boundary, leaving its signature in sediments, ice cores, and possibly in the collective memory of human survivors. Chapter 4. The Vanished World. The first compelling evidence for catastrophe appears in the fossil record. North America lost approximately 35 genera of large mammals virtually simultaneously around 12,900 years ago. These weren't isolated extinctions, but a continental mass dying unlike anything seen since the dinosaurs disappeared. Mammoths and mastodons, which had survived multiple previous climate shifts, suddenly vanished. Giant ground sloths, which had existed for millions of years, disappeared. The American lion, larger than any modern big cat, was gone. The pattern was one of abrupt, simultaneous collapse. For decades, scientists debated two main explanations: human overhunting, the overkill hypothesis, and climate change as the world warmed after the Ice Age. Neither fully explained the pattern or timing of extinctions. Something was missing from our understanding. A key breakthrough came when researchers began examining sediment layers precisely at the Younger Dryas boundary. What they found challenged conventional explanations and pointed towards something far more catastrophic than gradual climate change or human hunting pressure. In 2007, a team led by Richard Firestone published findings in the Proceedings of the National Academy of Sciences describing an unusual layer of materials at sites across North America. This black mat contained exotic materials not typically found in such concentrations in Earth's crust. Among these materials were nanodiamonds, including forms that require extraordinary pressure and temperature to form. There were magnetic microspherules, tiny balls of metal formed in extreme heat. Elevated levels of iridium and other platinum group elements typically associated with meteorites were also present. Carbon spherules suggesting widespread burning were found alongside evidence of continent-wide wildfires, a charcoal layer that appears simultaneously across vast distances. The pattern suggested an extraordinary event. Something had set much of North America ablaze all at once. The researchers proposed that Earth had collided with fragments of a large comet around 12,900 years ago. The multiple impacts or airbursts would have released energy equivalent to millions of nuclear bombs, triggering wildfires, atmospheric dust, and rapid climate change. Initially met with skepticism, the hypothesis has gained supporting evidence over subsequent years. The same impact markers have now been found at over 50 sites across 4 continents, all dating to precisely the same time period, the beginning of the Younger Dryas cooling. At Blackwater Draw in New Mexico, the type site for Clovis culture, these impact markers appear exactly at the boundary where Clovis artifacts disappear from the archaeological record. Above this layer, the distinctive Clovis points are never found again. A culture vanished. In the Carolinas and across the eastern seaboard, hundreds of shallow elliptical depressions called Carolina Bays point toward the Great Lakes region. Some researchers believe these may be secondary features from the impact, essentially splash marks from material ejected by the main event. At Göbekli Tepe in Turkey, the world's oldest known temple complex, Researchers have identified astronomical carvings that some interpret as depicting the constellation Scorpius with a comet strike. The timing of the site's construction, just after the Younger Dryas, may not be coincidental. Ice cores from Greenland show a sudden spike in platinum precisely at the Younger Dryas boundary. This anomaly, consistent with cosmic impact, was later found in ice cores from 18 sites across the northern hemisphere, suggesting a truly global event. Perhaps most compelling is the discovery of a thin layer containing impact-derived microspherules within the Greenland ice sheet itself. These tiny metallic spheres, requiring temperatures over 200 degrees Celsius to form, appear precisely at the layer dating to 12,900 years ago. The geographic pattern of these findings suggests multiple impacts centered on the North American ice sheet, with debris scattered worldwide. The pattern aligns with what we would expect from a fragmented comet striking Earth at an oblique angle. Critics have challenged aspects of the hypothesis, questioning whether all the material is truly impact-related or whether dating methods are precise enough to establish simultaneity. This healthy scientific skepticism has driven researchers to gather more evidence and refine their analyses. Several independent research groups have now confirmed the presence of nanodiamonds and other impact markers at the Younger Dryas boundary. The evidence has withstood scrutiny and grown more compelling as research techniques have improved and sample sites have multiplied. The human impact of such an event would have been devastating. Simulations suggest that airbursts over the ice sheet would have generated massive meltwater floods, hurricane-force winds carrying debris and sparking wildfires, and an impact winter as dust and soot filled the atmosphere. Archaeological evidence shows a significant reduction in human population during this period. In North America, the distinctive Clovis culture disappears abruptly from the record. In Europe and the Near East, many settlements show signs of abandonment precisely at this time. The few human groups that survived would have faced a transformed world. Colder, with many food sources suddenly vanished. Familiar landscapes altered beyond recognition. The psychological impact of witnessing such catastrophe would have been profound, potentially shaping cultural memory for millennia. Could this explain the remarkable similarities in flood myths and world-ending catastrophes in cultures worldwide? Stories of fire raining from the sky, worldwide floods, and destroyed previous worlds appear in traditions from Native American to Norse, Mesopotamian to Hindu. Ancient texts like the Younger Edda describe 9 worlds that burned, while Plato's account of Atlantis speaks of a civilization destroyed in a single day and night of misfortune. Aboriginal Australian stories tell of a time when stars fell from the sky and became black dust. Even more intriguing are accounts from the Book of Enoch, an ancient Jewish religious text which describes a great comet that split into 7 parts, bringing destruction. Though written down much later, such accounts may preserve memories of actual events passed through oral tradition. The implications are staggering. If these stories represent cultural memories of actual cosmic catastrophe, they constitute the oldest historical records we possess, predating writing by thousands of years. They would be humanity's attempt to preserve crucial warning knowledge across generations. As our investigation continues, we'll explore what happened to the survivors of this cosmic catastrophe. How did they rebuild? What knowledge did they preserve? And most crucially, what does this forgotten apocalypse tell us about our vulnerability to similar events today? But first, we must confront the most startling possibility raised by recent discoveries. Evidence suggesting this may not have been an isolated cosmic accident, but part of a recurring cycle, one that has shaped Earth's climate, triggered mass extinctions, and repeatedly reset human civilization. Chapter 5. History's Unexplained Gap. The conventional timeline of human civilization contains a puzzling gap. According to mainstream archaeology, humans existed as hunter-gatherers for nearly 200,000 years. Then, suddenly, around 10,000 BC, just after the Younger Dryas period ended, we see an explosion of development across multiple continents. This simultaneity presents a striking anomaly. In Mesopotamia, Egypt, the Indus Valley, China, and the Americas, complex societies emerged with remarkable speed. Agriculture, monumental architecture, astronomy, mathematics, and writing appeared in a relatively compressed time frame after millennia of apparent stagnation. The standard explanation attributes this to the stabilizing climate of the Holocene, which began around 9,700 BC. As conditions became more favorable, humans independently developed similar technologies to exploit their environments. But this explanation has weaknesses that are becoming harder to ignore. First, the transition was too abrupt. Hunter-gatherers had experienced favorable climate conditions during previous interglacials without developing agriculture or complex social systems. What made this time different? Why the sudden shift in human capabilities and aspirations? Second, the emerging civilizations shared puzzling commonalities despite supposed isolation from one another. Similar architectural techniques, cosmological concepts, and mathematical knowledge appeared in supposedly unconnected regions. The parallelism seems too precise for coincidence alone. Third, many of these first civilizations emerged with technologies and knowledge already fully developed. Egyptian architecture, Sumerian mathematics, and Mesoamerican astronomy didn't show the expected pattern of gradual refinement through trial and error. They appeared remarkably sophisticated from the start. This pattern suggests a troubling possibility. What we consider the beginning of civilization might actually represent a recovery. Survivors rebuilding with knowledge preserved from before a global catastrophe. The Younger Dryas Impact Hypothesis offers a framework for understanding this anomaly. Consider Göbekli Tepe in Turkey, a megalithic site consisting of massive carved stone pillars arranged in circles. Conventional dating places its construction around 9600 BCE, immediately after the Younger Dryas period ended. Its sophistication confounds traditional understanding of Stone Age capabilities. The site's builders possessed advanced knowledge of stoneworking, engineering, and astronomy, despite supposedly being pre-agricultural hunter-gatherers. The 20-ton pillars are precisely carved and positioned according to astronomical alignments. This represents a level of organization previously thought impossible for the period. Even more puzzling, after functioning for over 1,000 years, Göbekli Tepe was deliberately buried. Approximately 500 cubic meters of debris was carefully packed around the structures. Why would a pre-literate society invest enormous effort to preserve, rather than simply abandon the site? Similar anomalies appear at Gunung Padang in Indonesia, where recent geological surveys suggest megalithic structures may date to 9,700 BCE or earlier. If confirmed, this would overthrow the conventional understanding of technological capabilities in Southeast Asia during this period. In Peru, the Huaca Prieta site has yielded sophisticated textiles, evidence of agriculture, and complex architectural features dating to around 13,000 to 11,000 BCE, before and during the Younger Dryas. This suggests technologies developing just before a major interruption. The archaeological record shows something even more puzzling. Certain technologies appear, disappear, and then reappear thousands of years later. The concrete used in ancient Rome, for example, was superior to modern concrete in some respects, yet the formula was lost for centuries. Antikythera mechanism, an ancient Greek astronomical computer discovered in a shipwreck, demonstrates mechanical knowledge that wouldn't be seen again until the 14th century. Such examples suggest that human technological development hasn't followed a simple upward trajectory, but has experienced significant setbacks. Similar patterns appear with ancient knowledge of mathematics and astronomy. The precision of ancient calendars and astronomical alignments in structures worldwide suggests knowledge that was later lost and had to be rediscovered. This pattern of loss and rediscovery contradicts notions of steady progress. Even writing shows this pattern. The earliest examples of writing already use complex systems with hundreds of signs. We don't see the expected evolutionary stages of development. Instead, writing appears suddenly in already sophisticated forms, suggesting earlier developmental stages we haven't found or that were destroyed. Another contradiction lies in ancient megalithic architecture. Sites like Sacsayhuaman in Peru feature precisely fitted multi-ton stone blocks that would challenge even modern technology. The conventional explanation that these were created using simple tools and manpower strains credibility. The dating of the Great Sphinx presents another anomaly. Geologist Robert Schoch has documented evidence of water erosion on the Sphinx and its enclosure, suggesting it was carved when the climate in Egypt was much wetter, potentially thousands of years earlier than conventionally believed. If the Sphinx is indeed older than mainstream Egyptology maintains, it would imply an advanced civilization existed in Egypt before the officially recognized dynastic period. This earlier culture would have possessed the organizational capacity and technical skill to create monumental architecture. Perhaps most puzzling is the global distribution of advanced knowledge before reliable long-distance communication existed. The precise measurement of the solar year at 365.24 days appears in cultures worldwide. The precessional cycle of approximately 26,000 years was also widely known despite requiring generations of observation. The value of pi appears with remarkable accuracy in structures and texts from Egypt, Mesopotamia, India, and China. Complex mathematical concepts like the Fibonacci sequence and the golden ratio are embedded in ancient architecture across multiple continents. How did this knowledge spread so widely? Ancient maps present further contradictions. The Piri-Reis map, compiled in 1513 CE, but based on older sources, shows Antarctica without ice and with accurate coastal details. Modern science only confirmed these coastal features in the 20th century after radar mapping penetrated the ice sheet. The implications are profound. If the source maps for Piri-Reis were accurate, they would have required sophisticated surveying capabilities and suggest knowledge of Antarctica before it was covered by its current ice sheet, a process that began thousands of years ago. These anomalies collectively suggest our understanding of human history is incomplete. The conventional narrative struggles to explain the apparent sophistication of early civilizations, their surprising similarities despite geographic separation, and the pattern of technologies appearing, disappearing, and reappearing. The Younger Dryas Impact Hypothesis offers a framework that could resolve these contradictions. A global catastrophe around 12,900 years ago would have destroyed evidence of earlier advanced societies, leaving only the most durable monuments and fragments of knowledge preserved by survivors. As we examine these historical anomalies alongside geological evidence for catastrophe, a different picture of human history begins to emerge, one punctuated by disaster and recovery rather than steady progress. The implications challenge our understanding of who we are and where we came from. Chapter 6. Echoes in Myth and Stone. Throughout human history, across vastly different cultures, remarkably similar stories have been told about world-ending catastrophes. From the biblical flood to the Ragnarok of Norse mythology, from the Maya Popol Vuh to Aboriginal Australian Dreamtime stories, a common narrative emerges. These stories typically describe fire raining from the sky, worldwide floods, a long period of darkness, extreme cold, mass extinctions, and the near-complete destruction of humanity. Only a small number of survivors remain to rebuild civilization, often guided by knowledge preserved from the previous world. For centuries, these accounts were dismissed as primitive fantasies or attempts to explain natural phenomena through supernatural means. But, viewed through the lens of the Younger Dryas Impact Hypothesis, these stories take on a different character, as potential cultural memories of actual events. The Great Flood appears in over 200 different cultural traditions worldwide. While local flooding events could explain some of these myths, their global distribution and remarkable similarities suggest they might commemorate a shared catastrophic experience, perhaps massive meltwater floods triggered by the impact. In Plato's account of Atlantis, a sophisticated civilization is destroyed in a single day and night of misfortune when there occurred portentous earthquakes and floods. The timing he provides, 9,000 years before Solon's visit to Egypt, places the event remarkably close to the Younger Dryas boundary. Native American traditions speak of a time when the sky fell and stars fell to the earth. The Hopi describe the end of previous worlds by fire, ice, and flood. The Ojibwe tell of a time when the sun was darkened and a devastating cold followed. These align with impact winter conditions. The Lakotas speak of a time when a mighty serpent whose body was made from ice fell from the sky, causing massive floods and the death of most living creatures. The imagery of an ice serpent is suggestive of a comet's appearance, with its tail stretching across the sky. In South America, the Muisca people of Colombia tell of a time when the moon was not yet in the sky, potentially referring to a period when atmospheric dust blocked its visibility. After a great flood, their cultural hero Bakika brings civilization, teaching agriculture and social organization. Australian Aboriginal traditions describe a period called Nuala, when stars fell from the sky and became black dust, burning the land and causing floods as the oceans rose. The descriptions match what we would expect from multiple airburst events and subsequent climate effects. In India, Hindu texts describe the end of worlds or yugas through a variety of catastrophes. The Mahabharata contains passages describing a blazing missile possessed of the radiance of smokeless fire that resulted in a thick gloom swiftly covering the sky, followed by climate disruptions. Ancient Sumerian and Babylonian accounts tell of the god Enlil, who brought a devastating flood because humans had become too noisy. Behind this anthropomorphized narrative may lie the memory of actual floods following the impact event, perhaps connected to the rapid meltwater release from the North American ice sheet. Chinese historical records describe a time when the pillars of heaven were broken and the earth shook to its foundations. This was followed by great flames coming from above, and a period when the sun was obscured and the stars could be seen during daylight. These mythological accounts collectively preserve elements that correspond precisely to what we would expect from the Younger Dryas impact scenario. Initial devastation from fragments striking Earth or exploding in the atmosphere, followed by wildfires, floods, and a prolonged period of darkness and cold. The physical evidence for such a catastrophe exists in the geological record. The mythological evidence exists in our oldest stories. But there is a third category of evidence that bridges these domains: megalithic structures and artifacts that seem designed specifically to preserve knowledge through catastrophe. Göbekli Tepe's pillars contain carvings of animals, abstract symbols, and astronomical references. Recent analysis by engineers Martin Sweetman and Demetrius Sikritsis suggests specific carvings may record the cosmic impact itself, using animal symbols to represent constellations as they appeared 12,900 years ago. One pillar shows a vulture holding a sphere or disk, potentially representing the sun or the impactor above a scorpion. Computer modeling of the night sky in 10,900 BCE places the sun in the constellation we now call Scorpius during the summer solstice, precisely when the Younger Dryas began. This interpretation suggests Göbekli Tepe wasn't just a temple, but a commemorative site, a stone record of astronomical observations related to the catastrophe. Its deliberate burial might represent an attempt to preserve this knowledge for the future, protected from subsequent destruction. Similar astronomical alignments appear at megalithic sites worldwide. Many incorporate knowledge of the 26,000-year precessional cycle, a phenomenon requiring generations of precise observation to recognize. This suggests a sophisticated astronomical tradition predating these monuments. Even more puzzling are certain artifacts that seem wildly out of place for their time period. The Baghdad Battery, dated to the Parthian period, 250 BCE to 224 CE, consists of a ceramic jar containing a copper cylinder and iron rod that, when filled with an acidic liquid, produces electricity. The Antikythera mechanism, dated to approximately 100 BCE, contains at least 30 interlocking bronze gears that precisely model the movements of the sun, moon, and planets. This level of mechanical sophistication wouldn't be seen again in Europe until the development of astronomical clocks in the 14th century. In South America, artifacts from the Quimbaya culture made around 1000 CE resemble modern aircraft, with what appear to be wings, tail fins, and even landing gear. Aerodynamic testing has shown some of these ornaments would actually generate lift if scaled up. These out-of-place artifacts suggest technologies developed, lost, and redeveloped throughout human history. This pattern aligns with the catastrophist view rather than the gradualist model of steady technological progress. Knowledge rises, falls, and rises again as civilizations flourish and collapse. Perhaps most compelling are ancient texts that directly reference previous civilizations destroyed by cosmic catastrophe. Plato's dialogues, Timaeus and Critias, relate how Egyptian priests told Solon about civilizations that flourished and were destroyed before their own historical records began. According to these accounts, the Egyptian priests maintained records of everything great or splendid or remarkable that has happened, either in your country or in ours, or in any other region of which we are informed. These records allegedly stretch back 9,000 years before Solon's time. The priests explained to Solon, "There have been, and will be again, many destructions of mankind arising out of many causes. The greatest have been brought about by the agencies of fire and water." This cyclical view of history, with advanced civilizations rising and falling, aligns with catastrophist interpretations. Similarly, Mesoamerican texts like the Popol Vuh describe previous creations or worlds that were destroyed before the current one. The Dresden Codex contains what some scholars interpret as descriptions of cosmic impacts and their effects, including widespread flooding. These written accounts, alongside the physical evidence and mythological traditions, form a compelling pattern. They suggest humanity has experienced and recorded catastrophic events that reshaped our development. The most recent such event may have occurred at the Younger Dryas boundary. If true, this interpretation requires a fundamental rethinking of human history. Rather than a simple upward trajectory from primitive to advanced, our story may be one of repeated cycles, advanced civilizations developing, being devastated by cosmic or geological catastrophes, and then rebuilding from fragments of preserved knowledge. This cyclical view of history was common in ancient cultures, but was replaced by progressive linear models during the Enlightenment. The evidence now accumulating suggests our ancestors may have understood something about human history that we have forgotten or chosen to ignore. Chapter 7. Not if, but when. The evidence we've examined points to a catastrophic event, 12,900 years ago, that nearly ended human civilization before it truly began. But the implications extend far beyond rewriting our understanding of ancient history. They directly impact our present safety and future survival as a species. If Earth experienced a devastating cosmic impact in the geologically recent past, we must confront an uncomfortable truth. What happened once can happen again. The question shifts from whether such events occur to when the next one will strike, and whether our technological civilization is any better prepared. NASA's Center for Near-Earth Object Studies currently tracks over 28,000 asteroids and comets that cross Earth's orbit. Their models suggest impacts capable of regional devastation occur roughly every few thousand years. Civilization-threatening impacts might occur every 100,000 years or so. But these models assume even distribution over time. The emerging evidence suggests cosmic impacts might instead cluster in periods when Earth passes through debris fields associated with disintegrating comets. If true, impact frequency could vary dramatically, with multiple strikes possible within short timeframes. The torrid meteor stream associated with Comet Encke represents one such hazard. Earth passes through this stream twice annually, producing meteor showers in June and November. Astronomer Bill Napier has proposed that this stream contains larger fragments capable of causing Tunguska-scale events or worse. Disturbingly, several researchers have identified a roughly 7,000-year cycle in impact evidence. If this pattern holds, we may be approaching another period of increased cosmic bombardment. The most recent cluster would have occurred around the Younger Dryas boundary. The next could be due soon. Our technological civilization has never experienced an impact event larger than Tunguska in 1908, which flattened 80 million trees over 830 square miles of Siberian forest. That airburst, estimated at 3 to 5 megatons, was caused by an object only about 50 to 60 meters in diameter. By comparison, the Younger Dryas impactor or impactors would have been substantially larger, perhaps a kilometer or more across, or multiple fragments of a disintegrating comet. The energy release would have been thousands of times greater than Tunguska, enough to threaten global civilization. Our current planetary defense capabilities remain limited. While we've improved at detecting larger objects, we still miss potentially dangerous asteroids and comets. The Chelyabinsk meteor that injured 1,500 people in Russia in 2013 arrived with no warning whatsoever. If we detected a Younger Dryas scale impactor today, we would have few viable options to prevent disaster. Current deflection technologies remain largely theoretical. A large comet on first approach might be spotted too late for any meaningful intervention. The stakes are immeasurably higher now than 12,900 years ago. Today's global population exceeds 8 billion people, dependent on complex, interconnected systems for food production, energy distribution, and communication. These systems have minimal redundancy and little capacity to absorb major shocks. Modern agriculture relies on predictable climate patterns, extensive infrastructure, and global supply chains. A significant impact event causing even a moderate impact winter would devastate crop production worldwide. Current global food reserves would last only months. Our energy systems are equally vulnerable. The electromagnetic pulse from airburst events could destroy electrical grids across entire continents. The resulting blackouts would disable water treatment plants, fuel distribution, communications networks, and most modern transportation systems. Unlike our ancestors who lived in small, self-sufficient communities with practical survival skills, most modern humans lack the knowledge to produce food, purify water, or construct shelter without industrial support. Our specialization has made us more vulnerable, not less. The psychological impact might be even more devastating. Modern societies have experienced nothing comparable to a cosmic catastrophe. The collective trauma would overwhelm existing mental health resources and potentially trigger widespread social breakdown as systems fail. Historical examples of societal collapse suggest that once critical systems begin to fail, cascading failures follow. The fall of complex societies rarely occurs gradually. Instead, they tend to maintain apparent stability until crossing critical thresholds, then collapse rapidly and catastrophically. Yet despite these vulnerabilities, we've invested remarkably little in planetary defense. NASA's annual budget for detecting and tracking potentially hazardous objects is approximately $150 million, less than the production budget of a typical Hollywood blockbuster, depicting the very disaster we're ignoring. Even more concerning is our collective psychological denial. Despite scientific consensus that large impacts occur regularly on geological timescales, we treat them as science fiction rather than inevitable natural disasters. This cognitive bias leaves us unprepared for an event that will certainly occur eventually. This denial extends to how we interpret our own history. By dismissing evidence for past catastrophes, we blind ourselves to the cyclical nature of cosmic threats. We pretend Earth exists in isolation, protected from the violent realities of our solar system. The Younger Dryas Impact Hypothesis forces us to confront not just a reinterpretation of history, but our current vulnerability. If advanced prehistoric societies were devastated by cosmic impact, their fate foreshadows our potential future. Their story becomes a warning we cannot afford to ignore. What makes this particularly urgent is evidence suggesting we may be overdue for another major impact event. The historical record, combined with astronomical observations of the torrid stream, points to periods of increased bombardment occurring in cycles. We may be entering such a period now. In 2019, astronomers detected unusually large fragments within the torrid meteor stream, some potentially hundreds of meters in diameter. These objects, if they struck Earth, could cause devastation equivalent to thousands of Hiroshima bombs. And they represent only the fragments we've managed to detect. Even more concerning, a 2022 study published in Nature identified a previously unknown meteoroid stream that intersects Earth's orbit. Computer modeling suggests this stream resulted from a comet fragmentation event approximately 7,000 years ago, halfway between now and the Younger Dryas boundary. If the cyclical interpretation is correct, these discoveries represent precursors to an increased period of bombardment in the coming centuries. We may be witnessing the beginning stages of a process similar to what occurred before the Younger Dryas impact. The historical evidence suggests such periods don't necessarily manifest as a single large impact, but potentially as multiple strikes over decades or centuries. The cumulative effect of several Tunguska-scale events striking major population centers could be civilization-threatening even without a single massive impact. This perspective transforms how we should view the Younger Dryas evidence. It's not merely an academic question about the ancient past, but potentially a preview of our near future. The debate shifts from whether such events occurred to how we prepare for their inevitable recurrence. The survivors of the Younger Dryas catastrophe left us messages in stone and myth, warnings about the cyclical nature of cosmic catastrophe. At Göbekli Tepe and other megalithic sites, they encoded astronomical knowledge that might help future generations predict and survive similar events. These messages span millennia, preserved in durable materials and redundant systems. Stone monuments, oral traditions, and eventually written texts. They represent a sustained effort by our ancestors to transmit crucial survival information across generations despite the collapse of their civilizations. Yet we've largely failed to recognize these warnings for what they are. We've dismissed ancient accounts of cosmic catastrophe as mere superstition, rather than seeing them as attempts to preserve critical knowledge through cultural memory. We've ignored the astronomical encodings in ancient monuments. The most profound implication of the Younger Dryas Impact Hypothesis may be this. Our ancestors were more aware of cosmic threats, more dedicated to preserving warning knowledge, and potentially more advanced in predicting these cycles than we have acknowledged. If we embrace this understanding, it transforms how we interpret both our past and our future. We begin to see human history not as a steady march of progress, but as a repeating cycle of advancement, catastrophe, and rebuilding, with each cycle containing warnings for those that follow. This cyclical view was common among ancient cultures worldwide. From the Vedic yugas to Mesoamerican calendar cycles, from Norse mythology to Hesiod's ages of man, our ancestors conceived of history as cyclical rather than linear, with periods of flourishing inevitably followed by destruction and renewal. Perhaps most chilling is the possibility that we are not the first technological civilization to face this threat. Evidence of advanced knowledge in the ancient world, precise astronomy, sophisticated mathematics, and megalithic engineering hints at capabilities we've only recently rediscovered. What if previous civilizations reached our level of development or beyond, only to be devastated by cosmic catastrophe? What if the fragments of knowledge that jump-started post-Younger Dryas civilization were themselves remnants of earlier, more advanced societies lost to similar events? This perspective fundamentally changes our place in the human story. We may not represent the pinnacle of human achievement, but merely the current iteration in a cycle that has repeated numerous times. Our technological civilization might be one of many that have risen and fallen on Earth. The question becomes not whether we'll face a Younger Dryas scale impact, but whether we'll respond more effectively than our ancestors. Will we develop the necessary detection and deflection technologies? Will we create resilient systems capable of withstanding major disruptions? Most importantly, if the worst occurs despite our best efforts, will we preserve the essential knowledge future survivors would need to rebuild? Have we created durable, decentralized repositories of critical information designed to outlast catastrophe, as our ancestors apparently attempted to do? The answers to these questions may determine whether our civilization becomes a footnote in Earth's long history, another lost world dimly remembered by survivors through myth and legend, or whether we break the cycle by developing the capacity to prevent cosmic catastrophe altogether. Chapter 8. The Scientific Divide. No scientific hypothesis achieves consensus without rigorous debate, and the Younger Dryas Impact Theory has faced substantial criticism since its introduction. Leading scientists have proposed alternative explanations for the dramatic climate shift and extinctions that occurred 12,900 years ago. These competing theories deserve careful consideration. The most established competing explanation is the meltwater pulse hypothesis. According to this model, as the Laurentide ice sheet covering North America melted, enormous quantities of fresh water accumulated in glacial Lake Agassiz. Eventually, this lake catastrophically drained into the North Atlantic. This massive influx of fresh water would have disrupted the Atlantic meridional, overturning circulation, AMAC, the oceanic conveyor belt that brings warm water from the tropics to the northern latitudes. With this heat transport system shut down, the northern hemisphere would have rapidly cooled. This hypothesis has considerable evidence supporting it. Geological traces of massive flooding have been identified, and climate models show that such freshwater pulses could indeed trigger cooling events. Many paleoclimatologists consider this the most plausible explanation for the Younger Dryas cooling. However, the meltwater hypothesis struggles to explain several key observations. The abruptness of the cooling occurring within decades or less seems too rapid even for a catastrophic flood, and the presence of impact markers like nanodiamonds and platinum anomalies remains unexplained. Moreover, recent research has questioned the timing and routing of the meltwater discharge. Some studies suggest the primary outflow may have occurred through the Arctic Ocean rather than the North Atlantic, which would have had a much smaller effect on the AMOC. A second competing theory involves changes in atmospheric circulation patterns. This hypothesis suggests that as the northern hemisphere warmed and ice sheets retreated, wind patterns shifted dramatically. These changes could have altered ocean circulation without requiring a catastrophic flood trigger. Computer climate models lend some support to this idea. Simulations show that changing ice sheet configurations could indeed trigger reorganization of atmospheric circulation patterns, substantial enough to cause significant cooling, especially in the North Atlantic region. The main weakness of this hypothesis is that, like the meltwater theory, it struggles to account for the abruptness of the transition and the widespread impact markers. Atmospheric reorganization typically occurs gradually as ice sheets melt, not in the sudden manner observed in the paleorecord. A third alternative explanation combines volcanic activity with climate feedback loops. Some researchers have proposed that a period of intense volcanic eruptions could have injected enough aerosols into the atmosphere to trigger initial cooling, which then amplified through various feedback mechanisms. Volcanic cooling is well documented historically. The 1815 eruption of Mount Tambora caused a year without a summer in 1816. A series of major eruptions could potentially cause longer-term cooling, especially if they triggered changes in ocean circulation or sea ice extent. However, the geologic record doesn't show evidence of unusually intense volcanic activity precisely at the Younger Dryas boundary. While volcanic cooling likely played roles in other climate fluctuations, it doesn't appear to be the primary trigger for this particular event. Each of these competing hypotheses has strengths and weaknesses. What's particularly interesting is that they need not be mutually exclusive with the impact hypothesis. Multiple mechanisms may have worked together, with a cosmic impact potentially triggering or amplifying other processes. For instance, an impact on or near the Laurentide ice sheet could have accelerated ice melt, triggered massive flooding, and disrupted atmospheric circulation patterns all at once. This combined mechanism would explain both the impact evidence and the subsequent climate effects. The scientific debate has intensified in recent years as new evidence has emerged. Critics of the impact hypothesis have questioned whether the material identified as impact markers could have been formed through other processes such as wildfires or normal geological mechanisms. However, recent studies have strengthened the case for cosmic origin. High-temperature melted materials, magnetic spherules with extraterrestrial isotope ratios, and nanodiamonds with shock features have been found at dozens of sites across multiple continents, all dating to the same narrow time window. The debate highlights how science progresses through competing hypotheses tested against evidence. Each side has pushed the other to improve methods, gather better data, and refine explanations. This process ultimately strengthens our understanding regardless of which hypothesis prevails. Perhaps most importantly, the controversy has drawn attention to the vulnerability of Earth's climate system to sudden dramatic shifts. Whether triggered by cosmic impacts, meltwater pulses, or other mechanisms, the evidence clearly shows that stable climate conditions can change with frightening rapidity. This realization has profound implications for our understanding of current climate change. The paleorecord reveals that Earth's climate doesn't always change gradually. It can flip suddenly between different states when key thresholds are crossed, with or without extraterrestrial intervention. For proponents of the impact hypothesis, the controversy reflects more than just scientific disagreement. It represents a clash between catastrophist and uniformitarian views of Earth history, between those who see sudden, dramatic events as major drivers of change and those who emphasize gradual processes. This philosophical divide has deep roots in geological thinking. In the early 19th century, catastrophism, the idea that Earth was shaped primarily by sudden, violent events, dominated. This was later replaced by uniformitarianism, which emphasized slow, gradual changes over immense time periods. The pendulum has swung several times since. The discovery that an asteroid killed the dinosaurs revitalized catastrophist thinking. The Younger Dryas Impact Hypothesis represents a continuation of this reassessment, suggesting that catastrophic events may be more common and influential than previously thought. The debate also touches on human psychology. We tend to underestimate risks from events that occur rarely but catastrophically, while overestimating risks from more familiar dangers. This cognitive bias affects both public perception and scientific inquiry about cosmic impacts. Scientists on both sides acknowledge that large cosmic impacts do occur and have shaped Earth's history. The debate centers not on whether such events happen, but on their frequency, scale, and specific role in events like the Younger Dryas cooling and megafaunal extinctions. What makes this scientific controversy so compelling is that it concerns our recent past and may directly inform our understanding of current risks. If the Younger Dryas was indeed triggered by a cosmic impact 12,900 years ago, similar events could occur in the future. The evidence continues to accumulate on both sides. New analytical techniques are being applied to Younger Dryas boundary sediments. More precise dating methods are clarifying the timing of events. Computer models are simulating the effects of various proposed mechanisms with increasing sophistication. Ultimately, the question may not be which single factor caused the Younger Dryas, but how multiple factors interacted. A cosmic impact perhaps serving as the trigger for a complex cascade of climate and ecological changes that together transformed our planet at the dawn of civilization. Chapter 9. Beyond the boundary layer. While the debate over the Younger Dryas Impact Hypothesis continues, researchers have been making remarkable discoveries that extend beyond the boundary layer itself. These findings suggest the event may have been even more consequential for human history than initially proposed. Recent excavations at archaeological sites spanning the Younger Dryas period are revealing patterns of cultural disruption followed by innovation. At Tel Abu Herrera in Syria, evidence indicates the settlement was abruptly abandoned around 12,900 years ago, with analysis revealing melt glass consistent with extreme temperatures. When reoccupied later, the settlement showed dramatic changes in subsistence strategies, with intensified collection and eventually cultivation of wild grains. This pattern, abandonment followed by technological innovation, appears at multiple sites across the Middle East and is consistent with population displacement and adaptation. Similar patterns emerge worldwide. In North America, the sophisticated Clovis culture vanishes precisely at the Younger Dryas boundary, replaced by more regionally diverse adaptations. In Europe, the Magdalenian culture transforms. In East Asia, we see shifts in stone tool technologies. These simultaneous cultural transitions on different continents have traditionally been attributed to independent adaptations to changing climate conditions. The impact hypothesis offers an alternative: a global catastrophe forcing widespread cultural adaptation and technological innovation among survivors. Genetic studies provide another line of evidence. Analysis of both human and animal DNA reveals population bottlenecks, sharp reductions in genetic diversity occurring around the Younger Dryas period. These bottlenecks suggest dramatic population crashes consistent with a catastrophic event. Human mitochondrial DNA studies indicate several major haplogroup expansions beginning around 12,000 years ago. This pattern suggests small surviving populations rapidly expanded to fill ecological niches left vacant by the catastrophe, potentially explaining the sudden appearance of seemingly distinct racial groups. Perhaps most intriguing are new findings related to domesticated plants and animals. Genetic and archaeological evidence increasingly suggests that many domestication events cluster in the period immediately following the Younger Dryas, between 11,500 and 10,000 years ago. This clustering is difficult to explain under gradual adaptation models. Why would humans independently begin domesticating plants and animals at roughly the same time worldwide after hundreds of thousands of years of hunter-gatherer existence? The catastrophe model offers a compelling explanation. If a cosmic impact devastated existing food sources and disrupted traditional hunting and gathering patterns, surviving human groups would face intense pressure to secure more reliable food supplies. Domestication would provide precisely the stability needed in a post-catastrophe environment. Recent analysis of ice cores from Greenland and Antarctica has revealed another surprising finding: traces of a massive biomass burning event coinciding exactly with the Younger Dryas boundary. The data suggests continental-scale wildfires of unprecedented intensity. The scale of these fires exceeds anything that could be explained by normal climate processes or human activity at the time. The conflagration appears to have consumed significant portions of North America, Europe, and parts of Asia simultaneously, consistent with multiple airburst events. Equally significant are discoveries related to ancient structures that appear to have been built specifically to survive catastrophic conditions. Underground complexes like those at Derinkuyu in Turkey can shelter thousands of people and include sophisticated ventilation systems, water management, and food storage. Traditional dating places these structures much later, but recent reassessments suggest some portions may be significantly older than previously thought. Their design, specifically adapted to protect against surface threats, raises questions about what dangers their builders anticipated. Similar underground complexes exist worldwide, from China to Peru, many showing evidence of construction or expansion shortly after the Younger Dryas period. Their similarities, despite geographic separation, suggest a shared experience of catastrophe and similar strategies for future survival. The archaeological record reveals another pattern. Many early settlements show evidence of having been deliberately buried or sealed, preserving their contents for future discovery. Göbekli Tepe is the most famous example, but similar intentional burial appears at sites across multiple continents. This pattern suggests a conscious effort to preserve knowledge through catastrophe, almost like time capsules created by people who understood the cyclical nature of cosmic threats and wanted to ensure crucial information survived for future generations. The astronomical knowledge encoded in early monuments takes on new significance in this light. Many megalithic structures incorporate precise alignments to celestial events, including some that track very long-term cycles like the precession of the equinoxes and potential cometary return periods. Emerging research suggests these monuments may have served as both observatories and warning systems, allowing ancient astronomers to track and predict potential cosmic threats while preserving this knowledge in durable stone that could survive catastrophic conditions. The paradox at the heart of these discoveries is profound. The very catastrophe that nearly ended human development may have accelerated it. By disrupting existing patterns and forcing innovation among survivors, the Younger Dryas impact may have catalyzed the transition to agriculture and complex society. This creates a troubling implication. Our civilization may owe its existence to cosmic catastrophe. The technological path we've followed for the past 12,000 years, agriculture, urbanization, specialization, industrialization, might represent an adaptation to post-catastrophe conditions rather than humanity's natural development. If true, this suggests we've built our civilization on a foundation shaped by trauma and scarcity rather than abundance. Our current environmental and social challenges may stem partly from catastrophe-adaptive behaviors that became maladaptive once the immediate crisis had passed. This perspective transforms how we understand phenomena like resource hoarding, hierarchy, warfare, and ecological domination. These may not be inevitable aspects of human nature, but adaptations to post-catastrophe conditions, survival strategies that became institutionalized and persisted long after their necessity ended. The most profound paradox may be that the catastrophe simultaneously destroyed advanced knowledge while creating conditions that accelerated technological development among survivors. What was lost and what was gained in this crucible of fire and ice that forged our current world? This question leads to perhaps the most speculative but fascinating area of research: the possibility that advanced knowledge in ancient civilizations represents recovered rather than newly developed information, fragments preserved through the catastrophe by survivors dedicated to maintaining crucial wisdom. The sophisticated mathematics, astronomy, and engineering evident in early civilizations take on a different character when viewed this way. They may represent not primitive people making remarkable discoveries, but survivors drawing on fragmentary knowledge from more advanced predecessors. These paradoxes challenge our understanding of human development and our place in Earth's history. They suggest a more complex, cyclical pattern of advancement and setback, with cosmic catastrophes serving as reset buttons to both destroy and catalyze human civilization. Chapter 10: Ripples Through Time. And we began this journey with a simple observation. Around 12,900 years ago, as Earth was warming and ice sheets were retreating, something caused temperatures to suddenly plunge, thrusting our planet back into a deep freeze for over 1,000 years. Now we can reveal what the evidence truly suggests happened. The most compelling explanation for the Younger Dryas event is that Earth collided with fragments of a disintegrating comet. These fragments, likely multiple kilometers in diameter, didn't create a single large crater, but instead produced numerous airbursts and impacts across the northern hemisphere. The primary impact zone appears to have been the North American ice sheet, where the Laurentide ice sheet was still up to 2 miles thick. This explains the apparent absence of a single large crater. The impacts were absorbed by ice that subsequently melted, erasing much of the direct evidence. The energy released would have been catastrophic, equivalent to millions of Hiroshima bombs detonating simultaneously. The heat generated massive wildfires that consumed forests across continents. The evidence for these fires appears in the geological record as a distinct carbon-rich black mat. The impacts and resulting wildfires would have injected enormous quantities of dust, soot, and aerosols into the atmosphere, blocking sunlight and triggering rapid cooling. An impact winter similar to nuclear winter scenarios, but potentially lasting years or decades. Simultaneously, the impacts on the ice sheet would have released massive quantities of meltwater into the North Atlantic, disrupting ocean circulation patterns. This 1-2 punch, atmospheric cooling combined with ocean circulation disruption, explains the severity and duration of the Younger Dryas cold period. The ecological consequences were devastating. In North America alone, over 35 genera of large mammals went extinct, including mammoths, mastodons, giant ground sloths, and saber-toothed cats. These animals had survived previous climate shifts, but could not withstand the catastrophic pace of this change. Human populations worldwide experienced dramatic declines. Genetic evidence suggests population bottlenecks occurred on multiple continents around this time. Some cultural traditions disappeared entirely, while others were transformed as survivors adapted to radically altered environments. But this catastrophe did more than destroy. It catalyzed. The aftermath created conditions that accelerated human innovation. As traditional food sources disappeared, surviving groups intensified their exploitation of wild grains and eventually began domesticating plants and animals. The clusters of domestication events that appear in the archaeological record shortly after the Younger Dryas represent responses to catastrophic conditions, attempts to secure reliable food sources in a suddenly unpredictable world. Agriculture may have been necessity rather than innovation. The first known temples and complex ceremonial sites also appear in this post-catastrophe period. Göbekli Tepe, with its sophisticated stonework and astronomical alignments, was built by people who had just lived through apocalyptic conditions. Their monuments reflect both trauma and recovery. These early monumental structures served multiple purposes. They were astronomical observatories for tracking celestial cycles, including potential future impact threats. They were repositories of essential knowledge encoded in stone, and they were gathering places for rebuilding social cohesion among survivors. The myths and legends that emerged worldwide following this period reflect actual experiences preserved through oral tradition. Stories of fire raining from the sky, worldwide floods, and long darkness aren't primitive fantasies, but cultural memories of real events, preserved across hundreds of generations. What emerges from this evidence is a profound revelation. Human civilization, as we know, it was born from catastrophe. The transition from hunter-gatherer existence to agricultural society wasn't a natural, inevitable progression, but a response to cosmic disaster that forced adaptation and innovation. This revelation transforms our understanding of who we are and where we came from. The conventional narrative of steady human progress from primitive to advanced must be replaced with a more complex story of catastrophe and recovery, destruction and rebuilding, forgetting and remembering. Our most ancient monuments and texts take on new significance in this light. They aren't merely the first fumbling steps of emerging civilizations, but deliberate attempts to preserve crucial knowledge through catastrophe, warnings and guidelines for future generations who might face similar threats. The sophisticated astronomical knowledge encoded in early monuments reflects this imperative. By tracking long-term celestial cycles, ancient observers could potentially predict periods of increased impact risk. This knowledge wasn't abstract curiosity, but practical survival information. The similarities between early civilizations worldwide, their obsession with astronomy, their monumental architecture, their flood myths, reflect not coincidence or cultural diffusion, but common experience of catastrophe and similar strategies for survival and knowledge preservation. Perhaps most remarkably, this revelation suggests that what we call the beginning of civilization might actually represent a recovery period. Survivors, rebuilding with whatever knowledge they managed to preserve from before the catastrophe. We may be seeing not origins, but renaissance. This perspective resolves many archaeological anomalies. The seemingly sudden appearance of sophisticated knowledge, the mysterious abandonment of sites, the astronomical encodings in ancient monuments, and the universal myths of world-ending catastrophe followed by rebuilding. It also explains why early civilizations were so concerned with cycles of destruction and renewal. From the Mesoamerican calendar cycles to Hindu yugas, from Norse Ragnarok to Egyptian renewal ceremonies, cultures worldwide encoded the understanding that catastrophe is cyclical and preparation essential. This cyclical view aligns with emerging evidence about cosmic impact frequency. Rather than rare, isolated events, impacts appear to cluster in periods when Earth passes through denser portions of meteor strings. These periods of increased bombardment may occur in predictable cycles. If our ancestors recognized these cycles and encoded warnings in their monuments and myths, it raises a troubling question. Are we approaching another period of increased cosmic threat? Some astronomical evidence suggests the torrid meteor stream, which may have produced the Younger Dryas Impactor, is becoming more hazardous. The ultimate revelation is both humbling and empowering. Our civilization exists because our ancestors survived cosmic catastrophe and preserved crucial knowledge through dark ages. Their warnings and encoded wisdom weren't superstition, but vital survival information we've only recently begun to rediscover. What separates us from our ancestors isn't our superior knowledge, but our technological capacity to actually prevent cosmic catastrophe. For the first time in human history, we possess both the understanding to recognize the threat and the potential technological means to avert it. This capacity brings profound responsibility. We stand at a unique moment in human development, capable of either breaking the cycle of catastrophe or suffering the same fate as previous civilizations that reached advanced stages only to be reset by cosmic disaster. The choice before us is clear. We can dismiss the warnings preserved by our ancestors, or we can recognize the patterns they identified and use our technological capabilities to ensure that the next cosmic impact doesn't return us to the Stone Age. This isn't merely academic history. It's about our survival. The Younger Dryas Impact didn't just reshape our past. It reveals the challenges we must prepare for in our future. The question isn't whether another major impact will occur, but whether we'll be ready when it does. The greatest tragedy would be to ignore the warnings preserved at such cost by those who came before us, to dismiss as myth what they sacrificed to communicate across millennia. Their message, encoded in stone and story, is clear. What happened before will happen again. Our response to this revelation will determine whether our civilization becomes another layer in the archaeological record, a brief flourishing before catastrophic reset, or whether we become the first human society to break the cycle and achieve true cosmic sustainability. As we conclude our exploration of the Younger Dryas impact and its implications, we're left with a profound question. What will future archaeologists say about us? Will they wonder how we failed to heed the warnings preserved by our ancestors? Or will they celebrate our generation as the one that finally broke the cycle? The evidence we've examined suggests that cosmic catastrophes have repeatedly shaped human development, destroying, catalyzing, and transforming our path through history. These events weren't mythical but real, their consequences etched in stone, ice, and collective memory. Our ancestors went to extraordinary lengths to preserve this knowledge. They built monuments aligned to astronomical cycles, encoded warnings in myths and legends, and created institutions designed to maintain crucial information through dark ages. They understood what was at stake. We stand at a unique threshold. Unlike our ancestors, we possess both the scientific understanding to recognize cosmic threats and the technological potential to prevent them. We can detect incoming objects, potentially deflect them, and even develop sustainable space-based civilization as insurance against planetary disaster. Yet we've invested remarkably little in these capabilities compared to other priorities. We continue building civilizations with minimal resilience and maximum vulnerability. We dismiss ancient warnings as primitive superstition rather than hard-won wisdom preserved at enormous cost. Perhaps the most important lesson from the Younger Dryas impact is that human history isn't a story of steady progress, but one of resilience, of falling and rising again, of losing knowledge and rediscovering it, of civilizations growing from the ashes of previous catastrophes. The cycle can be broken. We can develop robust planetary defense systems, create decentralized knowledge repositories designed to survive catastrophe, build more resilient food and energy systems, and expand beyond Earth to ensure human civilization continues regardless of what happens to our home planet. The choice is ours. We can continue ignoring the warnings encoded in stone and story by those who came before us, or we can finally hear their message, carried across 12,000 years, and take action to ensure that our civilization isn't just another layer in some future archaeological excavation. If you found this exploration of our cosmic vulnerability enlightening, subscribe to our channel for more journeys into hidden history and the mysteries that connect our past to our future. Together, we can uncover the truths our ancestors preserved for us, and perhaps finally break the cycle they couldn't.